From this lecture, we will start clampers. In clippers, we saw various diode configurations that clipped off a portion of input waveform without changing the remaining part of the waveform. Now we will study different diode configurations that shift the applied signal to a different level. So clampers are the networks that shift the applied signal to a different level, whereas clippers are the networks that clip off a portion of input waveform. We can also define clampers as a circuit that places either positive or negative peak of the input signal at a desired DC level, or simply we can say that a circuit which shifts the DC level is known as clampers. This is much formal definition of clampers that you can note. A clamper is a network constructed of a diode, a resistor and a capacitor. In clamper network, we have a diode, a resistor and a capacitor that shifts the waveform to a different DC level without changing the appearance of the applied signal. So this is a formal definition of clampers, and all these things will be very clear when we solve this example. But before moving to this example, we have to discuss something very important. As you can see in this circuit, we have a capacitor and a resistor. So definitely there will be charging and discharging of capacitor, and tau, that is known as time constant of capacitor, is equal to R multiplied by C, where R is the value of resistor and C is the value of capacitance of this capacitor. So we have to find out the tau, the value of time constant, so that the capacitor must not discharge during the interval when the diode is off. In this circuit, you can see diode will be off or reverse biased for this negative half cycle. From T by 2 to T, the diode will be off. So we can say that for the half time period, the diode will remain off. So tau, the time constant, should be greater than the half time period of the waveform. Because if capacitor discharges during the half time period, we will not have the similar waveform. The waveform will change, and to avoid this, we must have the time constant greater than the half time period. Generally, for all the analysis, we assume capacitor charges or discharges in 5 tau, where 5 tau is the 5 times of the time constant. So this is what we assume for all the analysis, and this is very important. In various problems, you need to calculate the time constant first, and then you have to proceed to the other things mentioned in the problem. Let's solve this example. And this is very basic clipper circuit. We have one capacitor with capacitance equal to C. We have this diode, R is the resistance, and VO is the output voltage which we are measuring across the resistance R. VI is the input voltage, and I will analyze this circuit for the first half cycle. And you can see in first half cycle, from 0 to T by 2, the input voltage VI is equal to V. Plus minus will be the polarity. This terminal is positive, this terminal is negative for the first half cycle, because input voltage VI is positive throughout this half cycle. So from 0 to T by 2, the input voltage VI is equal to plus V, and you can clearly see the direction of current is clockwise. The direction of current is similar to the direction of arrow in the diode symbol. So this diode is forward biased, and I will replace this diode with short circuit because we are considering the ideal model of the diode. In case of constant voltage drop model, you have to replace it with the barrier potential. Now what will be the value of output voltage VO? In this condition, it is equal to 0 because there will be no current through the load resistance. This current will choose the path with the least resistance, and this path is having 0 resistance. So the current will flow through this path, and there will be no current through this load resistance. So VO is equal to 0. The output voltage VO is equal to 0 for the first half cycle, and we can see that there is charging of this capacitor, plus minus. This plate is connected to the positive terminal, this plate is connected to the negative terminal. So charge will accumulate like this, plus minus, and we have to find out voltage across this capacitor after the first half cycle. There is one very important thing that you can see. In this loop, there is no resistance. In this loop, the resistance is equal to 0. So time constant tau is also equal to 0, because resistance is equal to 0 and tau is equal to RC. If resistance is equal to 0, tau is also equal to 0. So the capacitor will charge immediately, and we can easily find out the voltage across this capacitor by using the Kirchhoff's voltage law. We have plus of VI minus of, let's say, voltage across the capacitor is equal to VC, minus of VC equal to 0. So voltage across the capacitor is equal to VI, and VI is equal to plus of V. So we have plus of V as the voltage across the capacitor. So V is the voltage across the capacitor, and for the next half cycle this voltage will remain there. The capacitor will remain charged because we have already assumed the time constant is greater than the half time period of this waveform. So capacitor will not discharge, and for the negative half cycle from T by 2 to T, we have voltage across the capacitor equal to V, and the polarity of input voltage will now change, minus plus, and also the direction of current, it is now anti-clockwise. The diode will be reverse biased, and I will replace it with the open circuit. There will be no current through this branch, and all the current will flow through the load resistance. Now we have to find out the output voltage VO by using the Kirchhoff's voltage law. I will move along with the direction of current, plus of VI, plus of VI, plus of VO, plus of VO, and we have plus of V, and this is equal to 0. So output voltage is equal to minus of VI minus of V. Minus of VI is equal to minus of V. So output voltage is equal to minus of 2V. This is what we have in the second half cycle, and we can easily plot the output waveform by using these values. I will change the color for this purpose. From 0 to T by 2, the output voltage is equal to 0. And for the next half cycle, from T by 2 to T, the output voltage is equal to minus of 2V. So it will look something like this. And you can see we have changed the level of DC voltage. Initially we were having minus of V, now we have minus of 2V, and the waveform is same, waveform is not changed. If I consider minus V as the origin, and consider only the green waveform, you will see it is similar to the white waveform. And if you consider minus V as origin, minus 2V will be minus V. So the output waveform is similar to the input waveform. The appearance of the waveform is not changed, only the applied signal is now shifted to a different level. So this is the use of clipper circuit. I hope it is clear to you. There are few points that you must note down. The first point is regarding the root mean square value. The root mean square value will remain same. The RMS value remains same. The clamped signal will have the same RMS value as compared to the input signal. The second point is related to the peak value. The peak value changes in the clamped signal. When you clamp a signal, the peak value will change, and we have already discussed about the time constant. Tau is greater than T by 2. So this is all for this lecture. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.